Hope you took your break, everyone. In my break, I got cracker things with Philadelphia. I made my coffee hot again. Okay, so this week we are sticking to our plan, our challenge, our 2-week challenge that we are a week into, which is to just finish the A-level spec. So even if, like, what that means is just like you've watched the video on it and made some notes, even if you haven't had time to practice it, at least you can see the whole spec. We did pure last week, and this week we're doing the stats and mechanics. So we've got 2 days on stats, 2 days on mechanics. Today is stats. We're going to do normal distribution. Then tomorrow, hypothesis testing, including correlation. So hypothesis testing for binomial, normal, and correlation. Then Thursday is going to be projectiles, I think, and Friday is going to be friction, something like that. Have a look at the schedule in the exambulance. Yeah, normal today, but I'm going to get started because it is not the easiest thing in the world until you realize that it is. Okay. So 45 minutes. Always have this on for 45 minutes. Or if you're super tired, do a 25-minute one. But having that timer and forcing yourself to stop it really keeps you focused. Every so often you have a quick look and it speeds you up and it keeps you focused and it stops you from procrastinating. And you think, well, I've only got 5 more minutes, so I'll try and quickly do this. It's really, really powerful. But you do have to get up in between and walk around and do stuff. That's why I went downstairs to get some Philadelphia. Okay, start. Right. So I've just been talking to the first years about the binomial distribution. And I will show you the page that I had for the binomial distribution. So the big thing that I was emphasizing to them is how important it is to write down whenever you do any question, even part A, part B, part C, that the thing of writing down what you're actually modeling. So it's the number of successes where you decide what successes is out of this many trials. And you have to write down what that is, and you have to write down what that is, and it really keeps you focused on what you're doing. Oh my goodness, integration, yes. Okay, I'll just tell you about binomial, and then I'll put some integrals down for you, I forgot. Right, and then there are some rules. So you should remember these rules from last year. You have to have a fixed number of trials, the trials have to be independent, the probability has to remain constant, and there has to be only 2 outcomes of each trial, okay? Those are the rules. And then there's this formula that you need to know for working out the probabilities of an individual thing. Now with normal, there's an equivalent thing, but it's slightly different. Okay, look at the difference between binomial and normal. So with normal, the thing you're measuring is not the number of blahs out of this many blahs. You're measuring something like length or width or weight or volume, that kind of thing, a continuous variable. And the thing that might change here, that might throw your answers off, is the units. So the volume in centimeters cubed, and then they set a question about meters. Okay, so by writing this down, including the units, if there are any, you're going to help avoid any particular problems. And with the binomial, writing down what it is that's a success and what it is that, how many trials you're doing, means that if they change the number of trials or change the thing that is success, you're always writing that down, you're always thinking about it. So it keeps you focused. Whereas in the binomial distribution, there are these clear rules for when you can use it. There are also the same rules for a normal, but it's more about how good the model is. So the normal distribution, the actual model, the mathematical one, has certain features. And what you're hoping is that your reality situation has the same features, because then the model will fit quite well. Okay. Katie, I will put it in the exambulance for the study hour later. I'll put it in the exambulance. So go in the exambulance and you know where it says schedule, right at the top of that page, I'll just put a link there on the schedule page, and it'll just say click here to join the study hour. And I'm just going to try it out, see what the difference is working inside the exambulance rather than doing everything streaming on YouTube. We're just going to see basically. Yeah, so these things here, they are kind of like rules, like with the binomial distribution, but really it's more how well the model fits. So if you've got something that is not symmetric, like you're more likely to get a high number than a low number, then it's not, the normal distribution isn't going to be a good model. If these things don't apply, the normal distribution isn't going to be a good model. And then just like with binomial, there's one formula you need that you use every so often. With normal, there's one formula that you need, and you use it when you don't know the mean or you don't know the variance. That's the only time we're going to use this. If you know the mean and you know the variance of the distribution, then you don't need Z at all. We're only going to use that where we don't know the mean, and I'll show you how to use it. Okay, right, I'm going to give you your integrals. Well done for wanting them. But I'm going to give you, to make it quick this time, I'm going to give you ones that you should just know. Okay, so this should be fast. One. Two. I'm trying to do this in my head. 3. 4. Okay. I don't mind this bit. A minute and a half more to think. Philadelphia is so yummy. The second one is defo not parts. Okay, 30 more seconds. Okay. Biscuit everywhere now. Right. These 4 are not the red 10. So I didn't do sine, cos, sec squared, or cosec squared, or cosec cot, or sec tan, or e to the, or a to the, or x to the n, or 1 over x. That's your basics. I didn't do those ones today. I moved on to the next level, but it's a standard way of pulling them back in. So your standard ones are sine squared x, cos squared x, tan squared x, and cot squared x. So all of these, you should just know how to change it into something that you can integrate, or you know what got differentiated. Sine squared is 1/2 1 minus cos 2x. Cos squared is 1/2 1 plus cos 2x. Tan squared is sec squared minus 1. And cot squared is cosec squared minus 1. And by using that identity, you just bang, pull it straight back into something that you can integrate. The other ones that were green that we were keeping an eye out for were the ones where you've got, there's 4 of them. You've got e to the something, and then you've got the derivative of the something at the front. Or you've got a fraction and you've got something down the bottom and then you've got the derivative on the top. Or you've got a trig function like sine or cos or sec squared, and then you've got something in there, and then you've got the derivative of that thing sitting at the front. And then there's one more example, which is the ones where you've got a thing to a power, and then you've got the derivative of that thing sitting at the front. And all of those, we can just write down the answer. So it's inspection or inverse chain is how you get them. So first one, standard, change it to sec squared minus 1, and then write down the answer. So I know what got differentiated because the only thing that differentiates to make sec squared is tan, so it must have been tan. This one, I'm spotting that it's this scenario. I've got e to the something, then the derivative. So I know what got differentiated. What got differentiated was that. If you differentiate e to the tan, you get e to the tan times the derivative of tan, which is sec squared. So that differentiates, and we're always thinking in that direction. We're always thinking about differentiating, never ever thinking about integrating. Next one, classic, it is this one. It's a fraction, and the bottom, when you differentiate it, you get the top. I'm going to have to do a tiny adjustment, but only tiny, it's fine. So it must have come from ln. Okay, when you differentiate that, you get 1 over x to the 4 minus 2x plus 1, and then you multiply by the derivative of the thing. Now, the derivative of that, if I actually differentiate that, I don't quite get this. The derivative would be 4x cubed minus 2. So it doesn't quite work. It will work if I double it, because then the 4x cubed would be 8x cubed, and the minus 2 would be minus 4. So if I double that, now it works. So a little bit of adjustment, just like I did an adjustment here. If you differentiate tan 4x add 1, you get sec squared 4x add 1, cool. But then you have to multiply by the derivative of the inside, which is 4, and I don't want a 4 there, so I put a quarter there, so that when that 4 comes out, it cancels with that quarter and there's nothing there. Notice that I am always differentiating, not integrating. But by differentiating and then looking, you get to see what it was. So the top one is a standard one. If ever you get an integral of tan squared, you immediately change it to sec squared minus 1, sec squared being one of the things that we know what it came from. Lastly, another standard one. Whenever you get cos squared or sine squared, you know what to do. You change it to a half minus a half cos, and then you double the angle. Double the angle. That's why I call them half double angles. In that direction, you double the angle. In the other direction, you halve it. So you have cos 2a is 2 cos squared a minus 1. So in this direction, you're halving the angle, whereas in this direction, you're doubling the angle. If I rearrange that, it says cos squared a is a half plus a half cos, plus a half cos 2a. And that's the exact same thing. I've just rearranged it. Exact same thing. So from here to here, I double, whereas from there to there, it halves. So all of the double angle formulae are actually half angle formulae as well. You halve in one direction, you double in the other direction. In this direction, you double. Okay, now we can write down the answer. 1/2 x plus 1/2 sine x plus c. Done. So if you found that exercise really difficult, you should have a look at what we did last week. I think it was Thursday. Well, every day last week we did a bit of integration, but on Thursday we went through all of integration and had a look at what it looks like and stuff. And the big thing to point out, as always, is that these ones are not parts. Just because there's two things times together does not mean it's integration by parts. Integration by parts is for the following situation. I'm going to get rid of all of this and make this very clear. parts. Situation 1, you've got something to do with learn. Situation 2, you've got a thing to do with X, and then you've got E to the stuff to do with X. Situation 3, you've got thing to do with X, and then you've got trig of thing to do with X. That's it. Okay, they're the situations in which you would use parts. Right, calculators at the ready. All of this is about calculators. Now, when I was talking to the first years about the binomial distribution, let's go back to the beginning so I can show you what was happening with the first years. This is what I was trying to make them do, write out this number line. So by writing out a number line and actually looking at the number line and seeing what the calculator is giving you and what you actually want, it can avoid loads and loads of the classic mistakes, okay? So that number line is really, really important. What I'm going to say to you about normal distribution, the equivalent is the picture. So always draw yourself a little picture before you use the calculator. Now, with the calculator, you've got two options. You're going into menu 7 if you use the class Wiz, or you're going into the statistics menu if you've got the CG, FXCG50 or FXCG20. And then you're going to choose normal, and you've got two options for normal. Well, no, you've got 3, but really there's only 2. You've got normal PD, normal CD, and inverse normal. You don't need normal PD. I don't even know what normal PD does compared with normal CD. No one has ever convinced me that it's a useful button. So we've got normal CD, and that is for less than or equal to. And we've got inverse normal, which is when we know the probability and we want the X. But it's all to do with less than or equal to. So either we're trying to find the probability that it's less than or equal to, or we know the probability and we're trying to find the X. That's the 2 buttons. And every single one, I'm going to draw a picture. And every single one, I'm going to identify what it is. So in this case, it is the length. Oh, doesn't say units. Cool. Because a really common thing is to put the units in and then in the question change it. Like, so here to say it's the length in centimeters, and then here do meters. So sneaky. But that's why I was looking for it. The length in what? So it's the length, and it's got mean 91, length of foil in meters. And the mean length of foil is 91 meters. And the standard deviation of the foil length is 0.8 meters. Okay, cool. So go into your calculator. Think about what you're trying to find here. So this 90 meters, that's what we know X, and we want the probability that it's less than or equal to. This one, we know X, and then we want the probability that it's less than or equal to. This one, we know X, and we want the probability that it's less than or equal to. So all of these ones are CD, not inverse norm, CD. CD is where we know the X and we want less than or equal to. So go into your calculator. Tell it that you want to find the probability. Tell it what the mean is. The mean is 90. I'm drawing it while you're telling the calculator. Standard deviation and variance, I remember it as variance squariance. Standard deviation squared is the variance. The variance is the square one, variance squariance. There we go. Right, so first one, the mean is not 90, the mean is 91. There's the mean. 90 is there. This scale is X, and I want less than 90. So I want this area here. So you just go straight to your calculator and you tell it in the calculator, you tell it that the You're in normal CD. You tell it that the mean, that's mu, is 91, and you tell it that the standard deviation, that's sigma, is 0.8. Tell it. Then say that you want the area to the left of 90. That's the x there. And it will always tell you the area to the left, unless you've got the Casio FX CG20 or CG50, in which case you can choose, do you want to the left or do you want to the right? But in the class whiz, it's only to the left. Okay, right, so that's not the right question. Here we go. So your answer to the first one should be 0.10565. I'll write it here. 0.10565 is that area there. And that's the answer. Next one. Now this is a sneaky one. Not exactly 90. Now with the binomial distribution, the probability of it being exactly 90, we'd be able to work that out. It would be the number of trials, choose 90, then the probability of success to the power of 90, and then the probability of failure to the power of 1 minus of number of trials minus 90. Yes, good point. You're all asking the same question. So isn't less than 90 and less than or equal to 90, isn't there a difference? There is in the binomial distribution. If you've got a discrete distribution, 89, 90, 91, if you do less than 90, then you get these guys. And if you do less than or equal to 90, then you get these guys. And what you've added on is the probability of it being 90, this guy here. And that probability is a real thing. It would be the number of trials, choose 90, times the probability of success to the power of 90, times the probability of failure to the power of n minus 90. That is what that number is, and that is a difference. But in the cumulative distribution being the normal distribution, that's the only cumulative one that you learn about, this guy is 0. The probability of an actual thing is 0. Our probabilities are areas, and the area of an infinitely thin rectangle, literally just on 90, not 90.1 and 89.9, literally just 90, the area of that stick is 0. So this makes no difference. I could do less than or equal to 90, or I could do like, I could draw it again and maybe try to communicate to myself that there's 91, that's the mean. I could go, yeah, but not 90, just up to 90. It will be exactly the same because the actual individual stick is 0. Okay, so what is the chance of it being exactly 90? 0. So what is the chance of it being something else, not exactly 90? 1. It's a trick question. It's making sure that you know that an individual thing has no chance of coming up. An individual thing, like just 1. So what is the area under the whole curve minus this one stick? It's 1. So that's a kind of trick question. Okay, next. I probably don't want to do that, but all right, I'm going to risk it and use the erase button. Please work, please work, please work. Yay. Okay. I. Always, always, always with the picture. Always. The mean is still 91. That's in the middle. That's the high point. It's symmetric. I want to be between 91 and 92.5. Okay. Now, no one actually asked me this, which makes me wonder whether you're doing it, but normal PD on the previous one. So I'm putting in X is 90 and the standard deviation was 0.8 and the mean was 91. Is that right? Yeah, the mean is 91 and press equals and it says 0.228, not 0.105. 2. Oh, I was in PD, not CD. Right. No one asked me about this. Was no one wondering what that bottom limit was on normal CD? Because it doesn't just ask you for the 90. It doesn't just ask you for the top. It also asks you for the bottom. So what is it that we put in the calculator? How do we get this 10565? We have to put something in the bottom as well. Yeah. Now, you can put in you can put in like minus a billion or whatever, but there is a general rule, and it's using this thing here. It's using one of the facts about a normal distribution. A normal distribution, basically all of the information, all of the data, all of the possibilities are within 3 standard deviations of the mean. Okay, exactly. But you can put in a massive small or a massive big, that's absolutely fine. But this fact about that you're meant to know about a normal distribution, it helps you to know what you could put in here. So what is the mean? 91. If I do 91, just in my normal calculator, 91 minus 3 times, what was the standard deviation? 0.8. Right, 88.6. Now, actually, I mean, I recommend we go lower than 88.6, right? But actually, by the time we get to 88.6, it's basically all done. That's how quickly it pulls back down, 88.6. So you will find that if you do the probability between 88.6 and 90, then you're going to get something really, really close. But the further left you go, the better it's going to be, because the further you've stretched it out. But you must be at least 3 standard deviations, ideally like 10 standard deviations away from the mean, to make sure that the amount of area that you're like not looking at is so ridiculously tiny that it doesn't matter. So we need that lower barrier as well. So I'd probably just put, yeah, like 0 or minus 1,000 or something like that. So that should get you your answer 0.10565. For the next one, it's much easier, because they've told you your lower bound, which is 91, and they've told you your upper bound, which is 92.5. So the answer that you get should be 0.46960. Okay, just between those two. Now, for the next bit, so that's the basics of how you use your calculator. We didn't try an inverse norm yet, but we're gonna try that in a minute. Okay, next one. I'm going to create some room here and show you how to do it when we don't know the mean or we don't know the standard deviation. This is what you do. It's basically the same. Okay, so you draw a picture. You draw your picture high enough up that you can draw 2 lines below it, Ronnie. Thank you. 1 line there, same as before. This is for X, and then another line here, which is for Z. And the reason that I'm doing these 2 lines is because I don't know the standard deviation. X is the length of the cling film in meters. X has a normal distribution. The mean is 153. But I don't know what the standard deviation is. Sorry, the variance. You put the variance here. I don't know what the variance is. Do not know. Now, when you don't know the standard deviation or you don't know the mean, then you need these 2 lines. And there's this connection between the X's and the Z's that is this formula here. And what we're going to do is we're just going to tell the yeah, it's called standardizing. And the only difference is that we are going to put this in the calculator because we can't put that in the calculator. That's literally it. That's the only difference. So we've got 153 as the mean, but we're going to be using Z, and Z has got a mean of 0. Okay. The question says that 1% of loo rolls, 1% loo rolls, I'm obsessed with them because all of social media is talking about loo rolls. 1% of the rolls of cling film should have a length of less than 150. So what does that look like on our picture? Here's 150. I'm keeping going using the Z thing as well. And this area here, this has got to be 1%. There. It's a pretty big 1% I drew there, to be fair. It looks more like 30 or 40%, but yeah, that's what it says. So we pick up our calculator because it's a normal distribution question, and every normal distribution question consists of a picture and then the use of a calculator, just like every binomial distribution question consists of a number line and then the use of a calculator. So we pick up the calculator. Now, what are we going to type in? Well, we're going to go, first of all, shift menu, and we're going to go 7 because, sorry, not shift menu, just menu 7. And then we're going to be like, right, is this normal CD or is this inverse normal? Inverse normal is where I'm trying to find the X and I don't know the probability. No, other way. CD is I'm trying to find the probability. Inverse is I already know the probability. And in this case, I do already know the probability. It's 1. So I press 3 for inverse normal. Okay, so we're carrying on. The calculator now says, what is the area? And it means the area to the left. So I can see on my picture, the area is 1%. So make sure you type this in right. Don't put 0.1, put 0.01, 1%. The area to the left is 1%. Now the calculator says, okay, what's the standard deviation? Now, this is why we're looking at Z, because if we're in the world of X, we do not know the standard deviation. We cannot put it in. So we are literally stuck at this point. So what we have to do is we have to pretend to the calculator that everything's fine. So we say to the calculator, oh, the standard deviation, that's 1. And the calculator says, what's the mean? And we don't say 153 because we're not telling the calculator about X. We're pretending it's all Z. And we say, oh, the standard deviation, the mean is 1. 0, the mean is 0. And the area is the area to the left. And then you press go and the calculator tells you the answer. Minus 2.3263. Make sure that you can get that and that you understand how it connects to the picture. The calculator's answering the question, but we have to pretend to the calculator that everything is in the world of Z, where the mean is 0 and the standard deviation is 1, so that we can get the calculator to answer the question. Okay, last step. These two, well, any two at all, the X on the top row, the Z on the bottom row, they are always connected by the same formula. The formula is that the Z number is equal to the X minus the mean divided by the standard deviation. So in this case, minus 2.3263 is equal to 150 minus 153 divided by the standard deviation. And that's how you find the standard deviation. Always the same steps. Always, always, always. Okay. So I'm going to give you about 10 seconds to use your calculator and find that answer. Okay, the answer is 1.28960. I mean, you would only need like 2 or 3 significant figures. Usually 3 significant figures. So yeah, 1.29 to 3 significant figures. Right, I basically have shown you everything you need. That's basically it. There isn't anything else to it. It's about the picture and using the picture. And then you know, by looking at your picture, you know what to put into the calculator. Okay, let's have a look at the next one. It looks really hard, but it's not. Okay. So what do we do when we start? We start by defining what X is. In this case, it's not called X, it's called W. And we don't know what it is because there's no context. So, you know, normally I would start by saying W is the length of blah, blah, but it's not the length, it's just W. It can be whatever you want it to be. It's just completely abstract. There's no context, which is great. So W is distributed normally. They tell us, and we don't know anything. We don't know anything. Right, picture. Because I know that I don't know, I'm definitely going to need this guy, for sure. Now, information that is important. The mean of W, but I don't know it, which is very sad, but I'm putting on the mean of the Z because that's what I'm going to use. I don't know. Okay, let's read it. Piece of information here. Now, what I want you to do is I want you to actually draw this, and I'm going to give you instructions, but I'm not going to draw it on. What I want you to do here is to put a vertical line on. And then I want you to label 70 on the W axis, where the bottom of the line is. And then I want, oh yeah, normal approximation we will do, yeah. And then when you've drawn your line down and put 70 on the W axis, I want you to read this and shade either to the left or the right, think about it. And label it 0.8. So you've got 4 options. Either your picture looks like this and you shade to the left, or you shade to the right, or your picture looks like this and you shade to the left, or you shade to the right. Those are the 4 options. And what you're trying to do is convert this information here to a picture. Only one of these 4 is right. Okay. Now I'm going to tell you straight away, I'm going to eliminate 2 of them because 2 of them are stupid, right? Number 2 is stupid and number 3 is stupid because the whole area is 1, right? The whole area underneath the whole thing is 1. So how can that possibly be 0.8 and and this bit's 0.2? It's just stupid. How can 0.8 be the smaller bit? It's stupid. So this is stupid as well because it can't be, it's neither of those. Okay. Right, now I want you on the same diagram, I want you to try to draw this. So you're going to put a vertical line. You maybe are going to use a different color for this. Draw a vertical line down, label 81 on the W axis, shade to the left or the right, and then label it 0.1. So again, you've got 4 possibilities for what my normal distributions are not very symmetric there, are they? You've got 4 possibilities. Either you did this, or this, or this, or this. 0.1, 0.1, 0.1, 0.1. Now, 2 of those are ridiculously stupid because 0.1 can't be massive. You can't have a massive 0.1 and then squish the 0.9 into that bit there. That's just stupid. So not that and not that. Okay. Now, we're going to use this information to find the 2 things that we don't know. We've got 2 things we don't know. We've got 2 pieces of information. Okay. Right, I'm going to catch you up now. Now, while I'm catching you up, I want you to think about using your calculator to find the Z values. So I'm going to draw it on what it should look like. You could do them on totally different diagrams. That might be easier. There's no real advantage in this case to putting it on the same one. W, Z, W, Z. And the reason I've got Z is that I don't know the mean. And also I don't know the standard deviation. The area to the 70 is 0.8. 70, 0.8. The area to the right of 81 is 0.1. 81, 0.1. And then put your little Z link things on as well. Oh, Sarah's got the Zs already. Yes, good. So this is really, really important that you can find the Z. So you go into your calculator. Do I want CD or inverse? Do I know the probability, in which case inverse, or do I want the probability, in which case CD? In this case, in both of them, you know the probability, so you can use inverse. Then the calculator says to you, okay, sure, what's the area to the left? And you say 0.8. Or careful, if you're in the other situation and the calculator says, what's the area? It means this, because it's asking you for the area to the left. Always, it just says area, but it means the area to the left. So be careful when you put that in. Calculator says, great, what's the mean? Now, obviously, we can't tell it that we don't know what's going on with W, so we pretend it's about Z and we say that the mean is 0. Then it says, what's the standard deviation? The standard deviation of Z is 1, so you put in 1. Then you press go and it tells you what your Z value is. So you now know this Z value and you know this Z value. And then in both of those cases, what we can do is join up the W and the Z, and always these join up with the same formula. So the formula is that the Z will equal the W minus the mean divided by the standard deviation. So in both cases, that Z value that you found equals the W, in this case 81, minus the mean divided by the standard deviation. And then in this case, it would be 70 minus the mean divided by the standard deviation. How did I get 0.84? I haven't got 0.84. No, I haven't. I haven't got any Zs yet. I didn't bother. I was going to let you do it. So you're going to get two equations there. The Zs are coming from your calculator. You should be able to get this Z and this Z, and then that goes there, and that one goes there. And then, as you quite rightly said, you use simultaneous equations. Now, I am going to jump straight to the simultaneous equationsy bit and tell you the answers, because this is really fiddly, right? But it's not what I want to be teaching you. It's just fiddly. So in this case, where is it? It is 150. No, it is 70 and 81. Yeah. Oh my goodness, I can hardly read it. It's so small. So the mean comes out to be 25. And the mean comes out to be 48.93. It's so small, I can hardly say it. And the standard deviation comes out to be 25, I think. Okay, right. Now the actual question. So don't worry about doing those simultaneous equations now. Flappy. The Z values that you should have got are 0.84, I can't even read it, 0.84 something to something, and 1.282. Yes, what Sarah said at the top, well done. So the mean is 48.96 and the standard deviation is 25. Yay! Okay, quickly, let's have a look at the actual question now. Here's the actual question. So again, draw the picture. It's literally picture, calculator, picture, calculator. Here's the picture, here's W. I now don't need Z because I know the mean and I know the standard deviation. So I know the mean, 48.96. I know the standard deviation. The question says that this thing here. So it comes down again to that vertical line. Put a vertical line on, label the bottom of the vertical line A. Shade either to the left or to the right of the vertical line, and then label that shading 0.1. You've got 4 options, as always. You could be on the right and shading to the right, or it could be like this, or it could be like this, or it could be like this. 0.1, 0.1, 0.1, 0.1. 2 of them are stupid. There's no way that's 0.1, it's too big. There's no way that's 0.1, it's too big. So it's one of those two. This is the one that you should have drawn. Go to your calculator. Calculator says, hello, do you know the area? And you say yes. So you choose inverse normal. And then it says, what is the area? And it means what's the area to the left? So you say 0.1. And then it says, what is the mean? And you say 48.96. And it says, what is the standard deviation? And you say 25. And it says, go. And then it tells you what A is. And that's the end. So A is 16.9. Picture, calculator, that's it. Right, the only bit that we didn't do is the using the normal to approximate the binomial. So this is a situation where you actually have a binomial distribution question, but you've got a massive N and you've got a P that's hopefully near 0. Certainly we need a massive N, otherwise it's not going to work. But your P should be somewhere around near 0, P being the probability of success, okay? So I am going to jump, because we've only got a minute, so I'm going to jump to this bit here. So what we've got at the beginning is, what's the situation here? Time taken for the person to do the test. 15 people. Right. Yeah, P near a half. Ideally, yeah. So this one here, does anyone know what I call these ones? I have a particular name for these ones. I didn't get round to it with the first years, but I told them to go look into it. Find the probability that fewer than 2 take less than 12. This is a type of question. And I call it a current bun question. Current bun question. It is, yay, it is number 55 in the course, AS lesson 55, which is free at the moment for the next 24 hours. So I call these current bun problems, and you can see current bun problems a mile off because they mention 2 different things. How can you be looking for less than 2 and also be looking for less than 12 in the same question? Okay, so they're always more than 3 were less than 10, or between 6 and 8 were bigger than 13. So you've got these 2 things. It's like, well, how do I combine the 2? So the way we combine the 2 is we go back to basics by writing out what M is and what X is. So M is going to be the time taken to do the test. That is a normal distribution. X is going to be the number of people who take less than 12 minutes out of 15. Now, a current bun question, is it could be a binomial inside a binomial, or it could be a binomial inside a normal, or it could be a normal inside a normal. But the point is that your probability, in this case, here, the binomial one, there's 15 trials, there's 15 people, there's 2 outcomes, either they are or are not taking less than 12 minutes, yes or no. Yeah, less than 12 minutes, yes or no, yes or no, yes or no. So what is the probability of that happening? Well, it's what we found in here, 10%. We didn't even have to work it out, they told us. So by defining it, it helps you to see what's going on. And this is what I was doing all the way through with the first year one with the binomial. Tell me what X is. X is the number of what's out of what. In this case, X is the number of people who take less than 12 minutes out of 15 people. So Graham selects 15 people. Find the probability that fewer than 2. Fewer than 2. X is fewer than 2. This is X. All it's asking me for is the probability that X is less than or equal to 1. So you go into your calculator, you say, calculator, it's binomial. I don't want an individual probability. I want less than or equal to. So binomial CD. The calculator then says to you, okay, what is N? How many trials are there? And you say 15. And it says, okay, what is P? What's the chance of success? Success is people who take less than 12 minutes to do the test, and the chance of success is 10%, 0.1. And then the calculator says, sure, what would you like the probability of less than or equal to? And you say 1. Then you press go, and it tells you the answer. So this one here is a current bun problem. It's got a normal. Well, actually, it doesn't even have a normal inside a binomial because they told us the P. Quite often, that P is what you've worked out earlier. But in this case, you didn't even have to do that because they just told you it. So this is a current bun problem. And this is in the first year course in the AS, it's the third of the binomial ones, current bun problems, if you want to have a look. I'm the only one that calls them current bun problems. So don't look for that in a book. I don't know what they're properly called. Right. Last thing, and this is where we're going to split up AQA and not AQA, right? There's only 2 things where AQA is slightly different. Moments, AQA no ladders. Normal distribution, AQA no continuity correction. Okay. This is why this is confusing, look. Using a normal approximation, find the probability that fewer than 9 take less than 12. Fewer than 9 take less than 12. Current bun, right? Fewer than 9 take less than 12. More than 8 do between 6 and 7. 2 different things. So it's a current bun one. So we really need to define our variables. That's what's going to be the key to everything. M is the time to do test. X is the number of people who take less than 12 minutes out of how many trials are there here? Well, when Graham did it, he selected 15 people. So it was the number of people who take less than 12 minutes out of 15. Now it's the number of people who take less than 12 minutes out of N. We don't know what N is. So far, this is all everybody, not just, I'll tell you when the AQA thing happens. Okay. So X, how is X distributed? Well, it's binomial. There's always 2 options. Either you did or didn't take less than 12 minutes. The number of trials is don't know. And the probability of success, the probability of less than 12 minutes is 0.1. Okay. What are we interested in? Fewer than 9 of the N people. So it goes 7, 8, 9, 10, 11, blah, blah, blah. Fewer than 9. So if we were putting this in our calculator, what we would put in is we'd put in N, we'd put in 0.1 for P, and then we'd say to the calculator, can you tell me the probability of less than or equal to 8? And it would tell us. Now, here's the problem. We don't know N, so we can't put it in. And also we know the probability, it's N that we want. So calculator cannot help here, okay? Now this is where, if it was normal and the calculator can't help, we just change it to Z. But this is binomial. We don't have a Z equivalent. We can't just change it to Z. And that's why we're doing the normal approximation. So how do you do the normal approximation? If something is binomial NP, then you can change it to being normal NP, NP1 minus P. And you can change the question to being a normal question where we have got an inverse button. That's what we're doing. So instead of normal NP, we're going to be changing it to, in our case, normal 0.1 N, 0.1 times 0.9 N. Okay, we still can't put it in the calculator though, because we don't know the mean and we don't know the standard deviation, so we can't put it in the calculator, but it's okay because with the normal, if we can't put it in the calculator, then it's okay because we can use Z. So it all comes together. So we draw our picture. We're drawing the normal. This is X. It's got a mean of 0.1 N. I don't know what N is. Here is Z. Z has got a mean of 0. Now, what on earth was I doing? I was trying to find this here. It's okay, I've drawn a picture of it, so everything is nice and clear. That's what I was trying to find, or rather, I know what that is. I know what it is. So what you do is you put a line, a vertical line, you put the vertical line on and you shade to the left because it's fewer than 9, and you label it 0.385, like this. No, this is not hypothesis testing. I'll do that tomorrow. So this bit here is 0.3085. And that number there, this is where AQA and the others differ. That number there for AQA is 8, because it was the probability of less than or equal to 8. Or you could use 9, because you could think of it as the probability that it's less than 9. AQA will take either 8 or 9. The other two will not. The other two, can you see what that's pointing at? What number would that be pointing at on an actual continuous number line? And then I have to go because otherwise Rich won't be able to start chemistry. Can you see that that's 8.5? So the continuity correction, the thing that AQA doesn't include and the other two do, all it is literally looking at your box that you wrote out for your binomial and just thinking, where's the line? Is it, what's it between what and what? And it's that 0.5. So 8.5. And then calculator, pick up calculator, tell the calculator that it's a normal, that you know the area, so you want inverse normal. The calculator says, what's the area to the left? You say 0.3085. The calculator says, what's the mean? You say 0 because we're doing Z. It says, what's the standard deviation? You say 1 because we're doing Z. You press go. The calculator tells you what this number is. You know what the connection between these two are. It's that formula there. So you write down, this is what the calculator just told me. X is 8.5 or 8 or 9 if you're AQA, minus the mean, which is 0.1n, divided by the standard deviation, which is the square root of this guy here. And then you rearrange and solve it for n. Ta-da! Okay, all of these questions are in the course. This is the master question. It was a hard one, but I wanted to push you with a hard one. I hope you've seen that drawing the picture and then using the calculator and using those two lines for N and Z, I know we are out of time, is all you need. Give it a go over the next 24 hours and I will see you 1 o'clock tomorrow for hypothesis testing.